Design of counters. At the end of this lesson, you will be able to define counter, explain the design procedure of counter, introduction to design of counters. Before heading into the topic, let us look at an analogy. Scenario 1. In a voting booth, there are counters at the entry gate or door. These counters count the number of people entering the booth. For entry of each person, the value of the counter increases by 1. Scenario 2. In our kitchen, we use microwave ovens. In that, we set the timer to heat food. You will notice that the timer in the appliance displays a gradual decrease in time as the food gets cooked or warmed. Scenario 3. In a washing machine, we set timer to complete an action, and you will notice that the time left to complete the action gets displayed. In all these scenarios, there is either a decrease or increase in the number displayed. These are operations which are done with the help of counters. Counter is a digital circuit which is used for counting pulses. In order to fit in these applications, we have to design the digital counters based on the requirement. Come on, let's discuss the design procedure of counters in this lesson. Design of counters. Let us discuss the design procedure of counters using a 3-bit binary up counter. The first step is to draw the state transition diagram. State transition diagram shows the sequence of states through which the counter advances when it is clocked. State transition diagram is used to describe the operation of the counter with a graphical specification. It is a graph with nodes and directed arcs, in which each node represents a unique state of the counter, and a directed arc connects two nodes representing the present state and the next state. If the counter is in the state at the tail of the arc, it will advance to the state at the head of the arc at the next count request. Once the sequential circuit is defined by the state diagram, the next step is to obtain the state transition table, which is derived from the state diagram. An alternative formulation of the state transition diagram is the state transition table, which shows the present state with the next state. Each row corresponds to an arc in the state transition diagram. The table represents the state transition table of 3-bit up counter. Each bit of the state is held by a single storage element. The storage elements are named as C, B, and A from the highest to the lowest order bit. Since there are 8 states, the number of flip-flops required will be 3. Flip-flops acts as the storage elements to store the bits. The next step is to choose a flip-flop type to implement the counter's storage elements. For example, toggle flip-flops are chosen for this state transition table. The truth table for T flip-flop is displayed. The inputs that must be presented to toggle flip-flops to implement the desired state transitions is displayed. It is obtained by comparing the present state and next state. Now, the next step is to transfer the states of the flip-flop inputs from the excitation table to Karnaugh maps to derive a simplified Boolean expression for each flip-flop input. The K maps for TC, TB, and TA are represented as shown. The expressions obtained from the K maps are obtained as displayed. Finally, draw the logic diagram of the circuit from the expressions obtained. the complete logic of a 3-bit binary counter is displayed. Using this design procedure of counters, we can design different types of counters. Conclusion. From this, we have understood the steps in designing a counter. Step 1. Draw the state transition diagram. Step 2. Derive the state transition table. Step 3. Choose a flip-flop type for implementation. Step 4. Express each next state bit as a combinational logic function of 3 current state bits. Step 5. Draw the logic diagram of the circuit from the expressions obtained. Summary. In this lesson, you have learnt about the design procedure of counters,